Good evening, everyone. Lovely to see you all. I've not been here for 22 years, but nevertheless, nice to see so many of you. Some faces I recognize, and also good to see some younger members in the audience. Delighted to welcome you all. I'm not giving an opening address, Richard. I'm just going to introduce Ken, the speaker this evening. So, many of you know, it is a real pleasure to introduce Ken, because he literally put the universe in this university. So Emeritus Professor Ken Pounds joined Leicester just 3 years after the university was granted the Royal Charter in 1960 and founded the Space Research Group. The first Leicester-built instrument in space was launched aboard a Skylark rocket in 1961. And there's been at least one piece of Leicester-built equipment operating in space every year since 1967. Since this first Skylark rockets, the University of Leicester experts have flown more than 90 instruments in space. There are currently 8 instruments operating in space that were either built by Leicester or with significant contributions from Leicester. The most recent of these are the Mercury Imaging X-ray spectrometer, currently on board ESA's Bepi-Colombo mission to Mercury, and the UK-led mid-infrared instrument for the James Webb Space Telescope. So when anyone asks what this university is known for, space research always comes as one of the top answers. And for that, Ken, we are very thankful. And also, all the others who have followed since. What you began over 60 years ago has literally taken off, and we now house Europe's biggest academic research cluster in space science and Earth observation. I was very pleased earlier this month, Professor Alan Wells, founding director of the Space Research Center, and Ken cut the ribbon on the state-of-the-art new Space Research Center at our space park. And if you haven't been there, I would certainly encourage you to pay a visit. Facilities include a 300 square meter clean room for the manufacture and testing of satellites and space instrumentation, plus specialized workshops and laboratories incorporating artificial intelligence, digital, and advanced manufacturing technologies. So Ken has made significant contributions to astrophysics and X-ray astronomy, and in this lecture, he will explore our space heritage by drawing on his personal experience in the field of space research in the UK. He will reflect on his continued contributions and provide an outlook on the future with the launch of our Space Park Leicester. This lecture by an esteemed and celebrated individual is part of our centenary celebrations, marking 100 years of Citizens of Change, of which Ken is a fine exemplar. Without further ado, I welcome Ken to deliver his lecture on our space heritage. Over to you, Ken.
Well, thank you, Nishan. In common with any introduction I get these days, I finish up feeling, am I really that old? Anyway, the setup is not familiar to me, although I did teach here years ago, in that I like to look at the same screen as you, but I'm looking at this one and I'm hoping you're looking at that one. There won't be any need to take notes, no exam at the end. It'll be basically a slideshow because I've got too much to do really by covering 60 years in 60 minutes. So you'll see anyway, starting off, that the subtitle basically covers what we do in X-ray astronomy, which is looking at the hot and violent things that are going on around the universe. And then in addition, in more recent years, we've expanded into looking at the planets, including planet Earth. So I'll hope to say something about all of that. So the summary of what I'm going to try to do is to start off with a brief comment about how it all started, both across the UK and here in Leicester. And then the following 60 years basically split into 3 sections of 20 years. The first is that between 60 and 80, we had a program that was largely funded nationally by the UK government, in which the facilities we used to get into space with the Skylark rocket or one or other of the aerial satellites. Then when UK funding shrank, I think the political decision was to do a kind of anti-Brexit and move into Europe, which we were happy with because it was clear that Europe together, in the form of ISRO or later ESA, would form a world-class capability. So we did that, and for the next few years we also seemed to become quite popular, and we had invitations to join other what we call bilateral missions with Japan, the United States, and Germany. I'll mention the Japanese one, which was a particular favourite of mine. And then the third and final era started in 2000, or 1999 actually, with the launch of 2 world-class open access X-ray observatories. In Europe, Xmm Newton; in America, Chandra. So that's what I'm going to try and do. And then if I get any time before you've mostly left, I want to just have a quick look at what's happening next, because I think we're all conscious at the university that we're now at the crossroads between our first century and our second century, which will be starting soon. And I hope I'll be able to get across in just a few minutes that we've really got a lot of exciting things ahead in space science. So the whole space around the world actually started with the launch by the Soviet Union of Sputnik, which was a small satellite about this big with a battery and a transmitter in it. It went around the world bleeping and caused a real shock, particularly to the Americans. A fairly rapid response from the United States was actually to Eisenhower persuading Congress to set up an organization called NASA, which of course still exists. And the Americans finally managed to do this in the right area. While all that was happening, here in the UK, there were actually things happening as well. I was an undergrad in a physics department from 53 to 56, and little did I know, actually, I had no particular interest in space or anything other than sport. And in the same building, in the physics department, there were talks going on by Harry Massey, who was the head of the department, and also physical secretary at the Royal Society, a very influential guy, about how we in the UK could prepare to do something for the International Geophysical Year, which was the target for all the scientific community in this kind of area, in 3 years hence in 1959. The focus in the UK was on the atmosphere. We wanted to know more about the atmosphere way above 30 kilometers, which balloons had previously been able to get to. And this was of interest also to the military, because some military strategists were thinking, well, you know, maybe the next wars will be fought in or through space, and so needed to know more about the properties of the atmosphere above the heights that could be reached with the balloon. Anyway, so there was a joint bid, which was presumably strengthened by this dual interest, coordinated by the Royal Society, and it had a fairly quick, as you'll see, response and positive response from the Treasury for £100,000 to do 2 things: to purchase the development of a rocket at the Royal Aircraft Establishment in Farnborough from an existing guided missile, and to fund 5 university groups for a 3-year programme. That didn't include at the time Leicester. Now, £100,000 doesn't sound much, but if you adjust it for reach our RPI, etc., it's several million. So it's a significant sum of money. Where I came into that is that from after graduating in 1956, I was invited to join the rocket group, which, as you'll see later on, we didn't actually have a rocket, but it still seemed to me a better option than leaving university and joining a firm called English Electric to become some kind of electronics person. So that, I should say, what was the real interest of the UK scientific community at the time? Well, it was to understand the Earth's atmosphere well above what you could reach with balloons. And my part in my PhD study was to develop X-ray instrumentation to fly above the atmosphere, which is the only place to be, of course, if you're interested in X radiation, because X-rays get absorbed in the atmosphere, knowing that it was very likely that the properties of the upper atmosphere, the density, winds, even ionization, would be controlled by heating from the sun, in particular X-rays that get absorbed in these higher regions of the atmosphere. And then also filling in the program, of course, was this acceptance of an offer from NASA to help other countries build and fly small satellites. So the whole thing started here in 1960, January 1960. This picture that had taken by the Leicester Mercury that I've shown quite a few times over the years was allegedly in the Fielding Johnson building. Bryn Cook, who was in one of this team, and he'd been an undergrad here, he said, well, actually, that was in the new physics building. But let's assume it was actually in the Fielding Johnson building, because it makes a rather nicer story. But the main point was the group was set up with the remit to do X-ray astronomy, to study X-rays from the sun, and if we could see any from anywhere else, then that would be a bonus. Came with a grant of 13,000 for a 3-year program. 13,000 again adjusted for RPI, etc., is somewhere between half and $1 million. So it was a lot of money because it didn't include staff salaries. Those were the days of dual funding, where universities in a program like this would be expected to find staff, and this grant, this external grant, was to just cover capital equipment, travel and things like that. So it was quite a substantial amount. I think at the time it was easily the biggest grant that the university had. Well, that photograph might not have been in the Fielding Johnson building, but this, I've got to show this. This definitely was. This is a photograph that was found by a colleague, Liz Blood, a while ago, and this shows a picture on the front corridor ground floor of the Fielding Johnson building. And that, what you're seeing is actually one student in the physics lab. Now, there were more, I don't know where the others were, but when physics started out in 24, 25, so we'll be getting our centenary quite soon, we had one lecturer, Menzies, and 10 students. And there's one of them, actually, you can see in his white coat. We don't wear those these days, of course. Right, so we're here at Leicester, we're starting. We have the benefit of a significant amount of money. We have benefit of a significant group of local people at the university, graduate students, a few members of staff, and some qualified technical people that we were able to recruit from the local industry, some of which stayed for a long time. And we were able to get our first equipment into space quite quickly by September the year after. And you'll see that's a picture of the rocket actually taking off at Woomera, Skylark 40. It actually got up to 153 kilometers. It carried a very simple X-ray, basically a steel cassette with film that was exposed to the sun from above the atmosphere through different filters. And our policy in the early days was to fly robust and simple experiments until we could develop, better reliability in the whole system. And that shows a picture of colleague Peter Russell showing me the results of exposing some photographic emulsion to the sun through different filters, aluminium, beryllium, and so on, which gives some spectral discrimination. And what we got was, at the time, believe it or not, that was the best picture of the solar corona that was around. Where you see on the right, basically, a picture of the sun. You're actually seeing the multi-million degree temperature of the corona, the bit you see during a total eclipse, with various active regions that are associated with enhanced magnetic activity in the surface. So simple things to do. Anyway, moving on, nationally, after the IGY, the UK joined the ESRO, which was this first organisation on operating on a European basis. And initially, the UK, because we hadn't suffered quite as badly as many other European countries during the Second World War, we were the major financial and scientific contributors in the first few years. I remember actually reading that Lord Hailsham, who was in charge of the space program, amazingly, a classicist, I think, from Eton. Anyway, he allegedly said he'd be willing to go over to Paris for the signing ceremony on behalf of the UK, provided a good lunch would be involved. So apparently he was promised there would be one, and he went. So at that time then, with access to Skylark, Ariel, and ESRO, the UK had actually built up quite a strong position by the mid-1960s. However, as you'll see, not everybody was happy with this, and there is a well-known story that Charles Clarke's father, Richard Clarke, sent a memo around the Treasury, as you can read it, asserting that for all we get out of the space program, we might as well spend the money digging for gold in the Outer Hebrides. Well, fortunately, that view didn't win the day, so the program continued. And our main job when we arrived in 1960 was actually to make sure we had the detectors that it was our responsibility for the first satellite, which was Ariel 1. And Ariel 1 finally took Leicester equipment into orbit for the first time, as you'll see, in April 1962, launched on a US Air Force Delta rocket. And the first, I think, of about 15 satellites to date where Leicester instrumentation has actually gone into orbit. We at the time were still working jointly with UCL. They had the engineering capability that we were still building up. So a joint X-ray spectrometer, which was based on one of the instruments I designed in my PhD, was on board Ariel 1, and we found that the solar X-ray flux was indeed strongly variable. You can see from that graph there 3 measurements of spectrum during the rise of a solar flare. And you could see from I hope you can, from the logarithmic scale on the left, that the X-ray flux at a few kV was changing during the flare by an order of magnitude. That was important for the atmospheric heating, of course. And I just mentioned something I learned just a few weeks ago, talking to my former colleague, Tudor Jones, who started out a little bit later and formed the department's ionospheric physics group. He said that it was having seen that graph that I showed him from Ariel 5 that he went along and spoke to the head of department. They decided that it would be interesting to correlate what we were getting from Ariel 1 with radio signals from the transmitter down at Rugby. And anyway, that went ahead, and it was the start of a new research group in ionospheric physics. Unfortunately, everything worked only for just over two months. And then our count rates went wild, so I thought, we got a short circuit. But it turned out that the US Air Force that had launched us, if you like, then came along and knocked us out. They'd, against all the international agreements, they had chosen to test a hydrogen bomb in the atmosphere above the Pacific, above Johnson Island in the Pacific. And that filled the Earth's magnetosphere with radioactive debris, and primarily a lot of soft X-ray, a lot of energetic electrons, which our detectors were sensitive to. So within presumably a few hours, our detectors were killed. And we found out later that 5 NASA satellites were also killed by this event. So clearly the liaison between the US Air Force and NASA at that time was suboptimal. There's a picture of the bomb going off taken from Hawaii, where what's happened there is that X-rays from the explosion have excited the oxygen in the atmosphere, so you can see red oxygen line emission filling up the sky. So that was the end of that, the end of Ariel 1. But by a remarkable coincidence, just a month before that Starfish Prime, and nothing to do with Amazon, by the way, that bomb, just a month before that, an American group led by a chap called Riccardo Giacconi, who I'll mention several times probably, they transformed the opportunities in X-ray astronomy by finding during a nighttime flight a bright point-like source of X-rays, which they didn't know what it was or where it was, but it was actually brighter than the sun at the time they looked at it. So this was a very interesting object. To cut a long story short, this source that became Scorpius X1 turned out to be a binary star system in which one component was a normal star, the other component was a neutron star. That's a star that's basically collapsed due to its nuclear fuel running out and collapsed down to the density of a nucleus. So it's basically just nuclei, mainly of hydrogen, crowded together in a region where you can get one solar mass into about 15 kilometers, so it would fit into Leicester. That, of course, gives you the potential for a very strong gravitational field. And so Scorpius X1, and it turned out to be one of quite a few of these, was an X-ray binary in which it was the strong gravitational field of the neutron star was pulling matter off the normal star. As the matter falls in, it's got a lot of gravitational energy which is transformed into heat. Hot, ultra-hot gas emits X-rays. So that's why basically Scorpius X1 is bright X-ray source. Now that for us was great because, we'd lost our solar satellite anyway, but we were thinking, well, the sun's fairly boring. And so we were really keen to get on to that. Riccardo Giacconi, as I mentioned there, was responsible for that first flight. That he became known as the father figure in X-ray astronomy. He quite rightly won the Nobel Prize in Physics in about 2002. We interacted with Giacconi's group at Harvard for basically the next 40 years. We won some, we lost some, but since he got most of the big calls first, he got the Nobel Prize and we didn't. That's my take on it. Anyway, so looking for other stellar sources, because Scorpius X1 couldn't be unique, could it? So we had the opportunity to look elsewhere, particularly in the southern hemisphere with Skylark. So that rapidly became our priority. And our plan was simple: get a Skylark rocket and fill the nose cone with a detector. In fact, 2 detectors, one looking both either way. And there you see the Skylark, the payload end, the rocket's not attached at the time. And this was down at British Aircraft Corporation, which had taken over the contract from Farnborough then. And one of the 2 guys there, the one on the left, Roger Cooper, is actually the one in that awful pink sweater. But anyway, thanks for all you did, Roger. And over 4 Skylark flights, 67 to 72, we actually were fortunate to find another dozen of these sources. And together with continuing activity in the United States, the situation was by the end of the 60s, something like 30 of these strange, highly luminous X-ray sources had been found. But what were they? There was really very little handle on what they were, except they were different from any kind of star that we'd seen before. I'll go on to what we did next in a minute, but just before leaving Skylark, I'll just show you this, because we carried on using Skylark for at least another 10 years. And that was a great program. I think we all enjoyed that. And there are 4 pioneering Skylark chaps there. And from the left, it's a research student, Barry Giles, Roger Cooper that I've already mentioned next to him, and then Roy Daldorf next to him. And then on your right is someone who'd come over on an international scholarship from Harvard, worked here for a couple of years, and then went back, joined NASA, and was one of the spacewalkers who saved the Hubble telescope from disaster, Jeff Hoffman. He's kept in touch with the university, and for quite a few years until recently did give an annual lecture to our undergrads. So that was obviously a fun time that those guys had with Skylark. I mean, I was stuck here by then, just writing grant applications and reports. But what were these remarkably luminous X-ray sources? As usual, we needed better data. And in particular, it would be important to find, are these sources variable? Because if they're variable, then you might be able to associate them with something going around in a binary system, or at least constrain the size of the region from which X-rays are coming. So fortunately, we had an opportunity fairly soon after that to go into orbit with Ariel 5, another in this series of small aerial satellites. As you can see there, launched from an old oil rig off the coast of Kenya with a Scout solid fuel rocket in October '74. You can see the size of Ariel 5 from the normal sized chap standing alongside. And we had 2 experiments on board. There were others from Birmingham, UCL, Imperial College. But by far the most productive was one of our 2, which you can see on the left, looking out from the side of the spacecraft, which was what we call a sky survey. The whole idea of that was, which was the creation of Bryn Cook largely, was to be able to look at and perhaps keep looking at the sky and just seeing what there was up there. So anyway, you can see there how heavy this thing was, and that it it was arranged to rotate around the spin axis at about 10 times a minute. It operated for nearly 6 years before re-entering the atmosphere. And, well, I think I already said who were the other ones on board. What made this project really exciting for all of us here was that we got the quick look data, a few orbits, almost instantaneously by a link that's shown on that graph there. The satellite was in an equatorial orbit, so it went over the same ground stations every 90 minutes. There were 2 ground stations that we could choose to use. One was on Ascension Island, and the other one, Quito in Ecuador. And the data then came back at not quite the speed of light, but quite quickly via NASA, Appleton Laboratory down near Slough, and up to Leicester. And then we were able to produce from that strip charts showing what there was that we were seeing. The amount of data is so incredibly small. I mean, a total orbit from this Sky Survey instrument, I think amounted, you can see there, 10, 24, 18-bit words for a whole orbit. I think an average tweet would have more data in it than that. But we made rather more use of that than most people these days. So the analysis, we also got the bulk data within 24 hours. The analysis carried out on a Cyber 72 large mainstream machine here in physics. And we had a team of enthusiastic young research students whose names are there. Quite a few of them became quite famous latterly. And their job was to monitor on a daily basis everything that was coming in. Quite early on in the project, in August, we decided that what we would do for a while is point the spin axis of Ariel 5 at the galactic pole, which meant the Sky Survey was going round and round the Milky Way, just to see what we could see. And remarkably, as you can see there, on the weekend of the 3rd of August, we saw something really quite remarkable. What was even more remarkable was that it coincided with a meeting of the European Astronomical Society at Stamford Hall. So we had a lot of the world's astronomers already on site, which did make it quite tense in a way. Well, you can see the plot of X-ray flux from this system. You can see the dates on the bottom. And after the initial discovery, you see that within a week or so, this source was brighter than SCO X1, and it carried on to almost 3 times as bright before it started to fade. So we had that record of the brightest ever da-di-da. Obviously, this object, whatever it was, became very famous, and observatories around the world, radio optical observatories, other satellites, was looking at this bit of sky to see what was going on. And we also had quite a bit of media attention, and with some embarrassment, hoping that you can't actually read the words, I'll show you that, because this was from the News of the World, which reassuringly quotes the head of the group with several inane comments. Basically, there's nothing to worry about. This has nothing to do with little green men, and if it's rushing towards us, I think I also say there, then it's not going to get here for a few thousand years. So calm down. That was my contribution. But in addition, more seriously, once the initial glow had faded, it was possible to turn a big optical telescope onto the companion star in this system, which turned out, of course, to be an X-ray binary. And these optical spectra showed that what we were looking at, by the way, that just the top bit there shows you that the X-ray flux essentially faded exponentially over a few months. But at the bottom, you see actually a measurement of line emission from the companion star with basically a Doppler shifted sine wave. And you probably can't see on the left, something like an amplitude of 500 kilometers a second. So what we were looking at, once the X-ray source had faded, was a star whizzing around nothing, because by then you couldn't see what turned out, of course, to be a black hole, at this enormous velocity, being held together by the strong field of this whatever it was in the middle. So anyway, to cut a long story short, to analyze the data, we were seeing a 7.8 hour binary, in other words, a very short-lived, short-period binary around some unseen companion. We were able to work out that what the mass of this unseen companion was, and it turned out to be more massive than the only alternative to a black hole, which is an object called a neutron star, which I've already mentioned. And more recent observations have actually shown the mass of this object was actually 6 solar masses. And it was in a binary association with a fairly normal, almost solar-like star. And looking back at old records, astronomers have been able to find that this fairly normal type star, which must have expanded at the time to dump matter onto the black hole, causing it to flare, that it actually does this periodically every 70 years or so. So if there are any of our new generation of space scientists in the audience, make a note in your diary, 2033, this is likely to happen again. Oh, just one final point. This black hole, which is quite famous because it's A, the closest we know of, 2,000 light years away. B, it's got the most tight constraints on the mass. Is also famous from the point of view that it was picked out by Stephen Hawking's daughter to receive a message all that way from 2,000 light years from the time when of his funeral at Westminster Abbey. So Lucy Hawkins has sent a message, and the name of this black hole is shown at the top, AO620, which is basically just its right ascension and declination in the sky. So if you want to tell your friends about that, that's what you call it. Now, there's one other thing that I want to just mention with regard to Ariel 5, and that is that we did, from the result of this 6 years of surveying the sky, we found a total of 297 sources altogether. That's a galactic coordinate plot, so along the what would be the equator if it was the plot of the geographical plot, all those big blobs are bright sources in the galaxy, which we see in the plane of the galaxy. But in addition to that, and really quite interesting, were lots of little dots, which mean relatively faint sources, which we didn't know what they were. I mean, they were either because of their uniform distribution, more or less, they were either very close or very far away. Anyway, detective work by people in the group here, led again by Bryn Cook, found that there was, despite the rather poor positional accuracy we had, which could be as much as a few tenths of a degree, and there's a lot of sky within a few tenths of a degree, we were able to find, by relating a large number of these sources, as many as 20 in the end, with bright Seyfert galaxies. So that was convincing evidence that, in fact, what we were looking at was, what we'd found, in fact, was an association of bright X radiation with a type of active galaxy. So what we were seeing were just normal Seyfert galaxies, and that again was one where we did rather better than RG, in that what Ricardo was trying to do was to argue with NASA that he needed a new big mission because they had evidence for different kind of galaxy. Well, Seyferts are not that different. I think he was thinking there may be galaxies out there somewhere which are full of X-ray binaries or something strange. Anyway, it turned out they were just normal Seyfert galaxies. You can see on the bottom right, I had the pleasure of telling the world about that at a meeting in Boston, just down the road from where RG was working, that this was the explanation. Anyway, the more important point is what made these Seyfert galaxies bright X-ray sources. Could they possibly be powered by a massive analog of AO 620, by, in fact, a supermassive black hole? Again, a key test was going to be variability. I mean, if the X-ray radiation was coming from the whole galaxy, it wouldn't vary on timescales, of a lifetime. But if it was something scaled like AO 620, it could vary on timescales of maybe days or maybe even less. We had just the satellite to give us a chance of seeing that, Exosat, but before launch, and I'll tell you about Exosat in a minute, but before launch of Exosat, we saw this discouraging paper published by a group at Goddard Space Flight Center. They'd also had this idea and been looking at a number of active galaxies with a big satellite they had called HEO-1. And they'd, as you can see from the title, they hadn't actually seen anything. So that was pretty discouraging, but nevertheless, Exosat, which was ESRO's or Europe's first X-ray satellite, which was advocated by us, and we really deserved then to get a good prize out of that. Exosat, you can see a picture there, included large X-ray detector, large X-ray proportional counter that you see covered in gold film on the left. And the special thing about Exosat was that it was in a very deep space orbit. It just didn't go around the Earth in a circular orbit. It went deep into space for an historical reason I won't bother you with, but that meant that we then had a satellite, because in a Keplerian orbit, as you'll all know, time with a source of mass here, then the thing goes very slowly up and over apogee and then whizzes round perigee and then do that again. So we had basically a satellite that was about to be launched that was going to be spending the best part of 3 days just sitting near the apogee. So we would potentially then be able to sit and look at sources with a really good coverage of time, and we found, in fact, a number of these bright Seyferts were incredibly variable. You can see the light curves there. You can see the time scale on the bottom, and that did seem to be a clincher that what we were seeing was, in fact, something analogous to the black hole that we'd seen in AO 620, but maybe 10 million times more massive, with a correspondingly large event horizon and correspondingly larger minimum size from which the X-rays could occur. So that, I think, persuaded that the astronomical community that in fact active galaxies were in fact powered by a supermassive black hole. There's an artist's impression of a supermassive black hole, and for me and other colleagues here, that was really a quite important moment, because it began a long period of research into these strange objects here at Leicester. At the same time, moving on from Exosat, we did have this great project with Japan, in which again we delivered the large X-ray detector, which was lovingly developed and delivered by one of our stars of the past, Martin Turner, you see there. It was a fun program to work in, because the Japanese were very non-bureaucratic. I mean, we got into it because they knew what we'd been doing with Exosat, and two leading Japanese X-ray astronomers just came to Leicester and said, would we like to help them building the detector? So we said, yeah, fine. And that was basically it. We shook hands and we went ahead and did it. They launched it, they'd built the electronics, and we had, during a period of 4 years, a really fascinating program in which people went from here to Tokyo, and there was an exchange of mainly graduate students coming the other way. So that was a fun program, and for a time that was the best X-ray satellite available for doing various things like measuring broadband spectra. I'd like to slip in an important aside here, that at that time we had developed quite a strong reputation for from the things we were doing in physics at Leicester. I was head of department around that time from the late 80s, and physics departments across the country were having real trouble on recruitment. Particularly girls weren't interested, apparently, in physics. My wife, who did physics at Durham, she said that wasn't really anything to do with hard maths, which you might have read somebody suggested recently, but was more to do with that physics was associated with electronics and nuclear physics and things that girls just did not find interesting. So we had the bright idea of changing the names of our degrees. So I agreed with Jack Meadows, head of astronomy at the time, to give joint degrees which would be physics with sexy things like astrophysics or space science and technology. And that was really successful, and it was copied by lots of other physics departments. You could see now that lots of physics departments have physics with whatever. Oh, well, that was all started here in the late 1980s. So we sorted out our recruitment problem, and better still, got a department that was much less like a department when I was an undergrad, 95% male. It had a really nice gender balance. And there's just a picture from a little bit later than that. This is in 1998, when I'd just come back from my 4 years of national service. I'm on the left at the front, several other people you can recognize, but the one I want to point to is the red-haired guy on your right, kneeling at the front. That's Will Marshall, who turns out to be quite a character, not least because he's the 27th removed nephew of the first Earl of Pembroke, who turns out, I was in like 1600 and something, and it turns out that the first Earl of Pembroke there's a book written on him in which he's described as Britain's famous knight, or something like that. Anyway, didn't discover that until later. What Will did was eventually, after he graduated in space science and technology, he moved to NASA, and from NASA he then went into, he got together with a colleague at NASA, and they developed this organization called Planet Lab. Planet Lab is a facility in San Francisco that was actually visited by our Chancellor when he was Secretary of State for Education. And what Planet Lab do is to, well, what they have done is to put several hundred small satellites in near-Earth orbit, all equipped with a high-resolution camera. And so they have the unique capacity, the unique capability at the moment of taking a high-resolution photograph of the whole Earth continuously. And, you know, the potential for that, for civil and military applications is enormous. It actually was put on the New York Stock Exchange in December last year, and immediately was worth something like $4 or $5 billion. So Will Marshall is of interest to our marketing department. And he will be coming to see us in the near future, I think. Oh, there's Will as he is now, and he's got over his shoulder, in his left hand, one of these small satellites that contains a camera. They're called Dove satellites. I think Will is one of these people who's very keen on protecting the planet and all of that. So I think Dove was carefully chosen. And I persuaded him to send a recent picture of Leicester just to prove we were in contact. And he sent one of the university. This is taken by a Dove satellite from orbit, from a few hundred kilometres above Leicester. And you can see the university campus there and Vicky Park, etc. That was on the 26th of March. Right, moving back to my main agenda then, the third of our 3 phases of research began in 1999 with the launch of the thing on the left, the Xmm Newton X-ray Observatory by ESA. But I show that together with another satellite, SWIFT, which was launched by NASA, because they at the moment are the 2 operational satellites that we're working on. Xmm Newton is the biggest satellite ever, X-ray mission that's ever been built so far. You can see some of the details there. Dick Willingale, chap sitting there with his arms folded next to an attractive-looking young lady. Shouldn't say things like that these days, should you? Anyway, I'm sure you don't mind. I know. Well, you can see the scale of XMM by the chap standing alongside. And our role in that, with the proportional counter that emerged from my PhD degree now being basically offset as old-fashioned, what we have there was an array of CCDs to do the same job, basically to collect, but also produce an image. And so we have another man in the same row, actually, Tony Abbey, who was involved in that machine on the left. So we'd really moved up again, but still having this Leicester tendency to build detectors. What did we do with XMM? Well, XMM, as I said, is still working as well as ever, and it's still, I think, the best X-ray mission there is, not least because it's kept me out of trouble for the last 20 years, in that when I came back to Leicester in 98, it was just before XMM was launched, and fairly early on we were able to make a discovery of something quite unexpected, in that we're always told that black holes swallow things up. So if you were looking at a black hole and you were seeing material on between the black hole and you, you'd expect if it was moving, it would be going in. But what we found was there were a lot of these supermassive black holes in AGN that actually were doing the opposite. They were driving off excess matter as a high velocity wind. By high velocity, I mean like 2/10 the velocity of light. And so that discovery of overfed supermassive black holes is something that I think Andrew King, a colleague of mine in theory group, and I have basically laid claim to for over the last 20 years. So that's been quite fun, keeping me out of my wife's hair some of the week. But in addition to that, Mike Watson, who's been running the Science Survey Centre for Xmm Newton, periodically produces a map of all the sources that have been seen. Now, this is rather out of date now. So this is a pre-COVID map, but already you can see 375,000 X-ray sources, and from a tiny part of the sky. So, we're looking now at a total transformation from the 30 sources in the rocket age to the 300 in the Ariel 5 age to now countless. So there is a lot. I mean, no one's ever going to look at all of these, of course, but I mean, there's plenty to be doing for an X-ray astronomer over the next life or two. Let me say something briefly about the other one that's currently operating, the other X-ray mission that's currently operating. It's an intriguing satellite called SWIFT, which is NASA launched, which has got an X-ray telescope that's built by the Europeans, where the mirrors are being built, provided by the Italians, and detector, of course, by us. This is a satellite that is equipped with a gamma-ray burst detector. Gamma-ray bursts were first seen by the US Air Force, of course, in looking for people who were cheating, and they thought, we want to see if the Russians are cheating by exploding nuclear bombs in the atmosphere. Well, it turned out they were doing it. But they did, and they were doing that by launching satellites called Vela satellites in the 60s, capable of looking at the gamma-ray flash from an exploding nuclear bomb. Well, anyway, that started the scientific interest in these gamma-ray bursts, and SWIFT is now, and has been since 2004, operating and looking for gamma-ray bursts. They see like one or two a week, and the origin is quite fascinating. Well, there's more than just the origin, but it seems like these gamma-ray bursts, which are the most powerful event since the Big Bang, which SWIFT is seeing from all around the universe, like I say, at the rate of about one every week or two. And what is interesting to me is that in the two theoretical ideas that from which gamma-ray bursts can derive, one is that a massive star just collapses and a large amount of material is thrown off in a gamma-ray burst. A more intriguing possibility, which I've now got a simulation of, is two neutron stars that have got captured into an orbit. So you've got two neutron stars, obviously pulling towards each other fairly dramatically. And what I've got to do is press this. Oh dear, that didn't work, did it? I was warned, actually, don't try but I'll try again anyway. Yeah, what you're seeing in almost real time are two neutron stars, remember about the mass of the sun, going round ever more quickly, eventually with an orbital period of less than a second, colliding. The mass of each neutron star exceeds what nuclear structure can sustain, so it finishes up as a black hole with the mass of the two neutron stars added together. And you noticed, I hope, that when this happened, the outcome was a beam of radiation. And that's the radiation that we see if we happen to be looking down the direction of that jet. And the energy involved in that is really incredible. I mean, like, I won't give the units because it probably won't mean very much, but a typical gamma ray burst emits in a few seconds the amount of energy that the sun will have radiated over its whole lifetime. So it is therefore not surprising that these events can be seen from wherever in the universe they happen to be pointing their jets in our direction. So what we're basically, I'll come on to this in a minute, but what we're basically seeing with these gamma ray bursts is the birth of a new black hole, a stellar mass black hole, somewhere in the universe, and it can be, it's within our universe, but somewhere, probably quite a long way away. It might occur to you, well, are any of these in our galaxy? Well, so far none have been seen in our galaxy. The prediction is in a galaxy we might see like 1 in a million years. That's probably a good thing, because if we were in the line of fire of a gamma ray burst in our own galaxy, it would be bad news. I think the atmosphere would probably protect us from the gamma rays and the X-rays, but the ultraviolet flash would probably cause us all to get very serious sunburn, if not more. So I think that I've now got to the point of running out of time. I apologize for that. But my last slide basically is to just now look ahead. I've been going around in the last few weeks as I was preparing this talk, seeing what was going on in some of the nooks and crannies of the department. It's been really heartwarming. I say there, it is brilliant to find a new generation of space scientists based here or down at the space park that are developing different kinds of space missions. And I think that makes the future look really bright. It does raise a question about, the management issues to do with some people being down there and some people up here, but I'm sure that can all be managed by people like Richard. And so as my almost final slide, then I've simply listed a number of space missions that are now on approved and will be going ahead. The first one, which is the only one I'll show you any detail for, is the one that's already en route to Mercury. This is Bepi Colombo, launched in 2018. It's now on a highly complicated route to get from the Earth all the way downhill under the sun's gravity to Mercury, to little Mercury, and having lost enough energy to actually able to go into orbit around Mercury. That's a challenge, and it does involve 2 flybys of the Earth. So it set off in 2018. 6 months later, it came back to the Earth. And then I think there are 3 flybys of Venus, all of which are to break it, because if you fly past, the idea of flybys is well established. And basically, what it means is that if you've got something going towards a massive object like a planet, it spends more time being decelerated on the way out than accelerated on the way in, so actually takes energy, transfers energy from the satellite to the planet. And the planet won't, of course, notice. So Bepi Colombo has been on its way for 4 years. It'll take another 3.5 to get there, arriving and going into orbit, hopefully, at Mercury. Followed in 2023 by an Eastern L class, which means large, multi-billion euro mission, JUICE, which people here are very much involved in. JUICE is basically a mission to Jupiter, and in particular to look at the moons of Jupiter. Of special interest, I think, is Ganymede. Say there that JUICE gets to Jupiter in about 2031 and then goes into orbit around Ganymede about 3 years later. 2 small satellites which are both in collaboration with the Chinese Academy of Sciences and launched by the Chinese, both looking at gamma ray bursts and filling in the kind of information that we get from gamma ray bursts, in which we have a common contribution to that and to Bepi Colombo, I'll mention in a minute. Followed by which there's a Leicester-led mission, part of the ESA program, called SMILE, which for the first time will take a satellite with an X-ray camera way out into a long way from Earth to look back at the Earth's magnetosphere and look at the way in which it's affected by the solar wind banging into the magnetosphere. That'll be a really interesting one. And then finally, ESA's second L-class mission also happens to coincide with a primary interest at Leicester. This is an X-ray mission, the ultimate X-ray mission, I think, to date, in which Dick Willingale has been involved, Mike Watson too, where ESA will be leading, NASA and JAXA, the Japanese Space Agency, will be in support, contributing instrumentation. That's due for launch, and this might be a challenge for me. That's due for launch in 2035, which will actually be in my second centenary. My second century. Thought I'd mention that to Vice Chancellor just in case he has any plans for my future. Well, I've almost finished. This is the only one I'm going to, of these new missions I'll show you any detail of. This is Bepi Colombo. It's actually, the PI is Emma Bunce, the head of physics, with other people involved, Susie Imber, our trainee astronaut, Charlie Fellman, young student, and Adrian Martinell, new lecturer. And the payload consists of 2 X-ray telescopes. The one on the left is a conventional Volta X-ray telescope. The one on the right is the new one. It's based on a design by a colleague of ours, now no longer with us, unfortunately, George Fraser, which is based on the optics of a lobster's eyes. And this lobster eye optic, X-ray optic, is in fact also used on most of the, I think, all of the missions. I think all but one of the missions I've talked about earlier on. So I have to show a picture of George Fraser. He was here for the whole of his career. He came from Aberdeen, did a PhD in X-ray astronomy, and then stayed on and became Professor of Detector Physics. And as I've said then, an inspirational director of the University Space Centre. Fine teacher, brilliant physicist, good friend, 35 years at the university, died far too young. And George was the one that basically invented this new X-ray optic, the point of which is that it has a wide field of view. So whereas a Volta telescope, like for instance on the Einstein, on the Xmm Newton mission, has high resolution but only sees about a degree of sky. In George Fraser's lobster eye optics, then you can see a much wider area of sky, albeit with less resolution, but ideal for looking for things like, where was that gamma ray burst? Looking at the range of across the magnetosphere, looked at from outer space. So anyway, I hope George is actually looking down and seeing that I've not forgotten him. Well, I want to end now, but I want to end on a lighter note, because that was a bit sad. And just to make the point that it has been fun looking back. We've had challenges, obviously, but I think most people that I talk to who've been here over the years, over the last 60 years, have said it was, maybe the best time they've had in their careers, which is nice. I want to show just one occasion here with a link to the future missions. In that, the guy on the left, we had a pop group years ago. I didn't name it, but they decided to call themselves King Awful. And the King Awful rock group, for which you see a photograph there in 1992, on lead guitar, the guy on the left was Paul Nandra, who, the modern version of which is now a suited, smart-looking chap who's the director of the Max Planck Institute and the principal investigator for the big wide-field camera instrument on Athena. So I'm going to keep this safe, this picture, in case we need any leverage on the PI of Athena in the future. The girl on the right is a graduate student working on exosat data, Lorraine Breeden. The chap on the far right, it was at the time working in condensed matter physics group. And my final message to any of this younger generation I've referred to that might be here or looking in a bit later on the recording is just two things really. Be lucky, because nature is so overwhelmingly variable that you can get to somewhere like Ganymede, and then you might find something really interesting, or you might not, and that's all up to, well, of course, the instrumentation working, but nature coordinating. Riccardo Giacconi was very lucky. On the other hand, he deserved to be, because with hindsight, if we'd, instead of flying small detectors to look at the sun, if we'd put one of Roger's big detectors and flown it at night time, who knows what we might have seen before he saw Scorpius X1. But you win some, you lose some, as they say. So be lucky, but also have fun, because it's a privilege to be working in an area of research where you have the chance to go places and do things that no one else has ever done before. And I think that's the message I would like to pass on to the next generation, that enjoy yourselves and be lucky and just find out more about things that no one else has ever seen before. So I'm sorry if I've overgone or just about on time plus 2 minutes, Chairman.